Okay, greetings, friends. Well, if you're watching this on the recording, you have no idea, but we're finally ready to go. It's been a little setup here as we've gotten the camera, we've gotten the speaker, we've got the little computer, everything's good to go. It is Tuesday morning, and we are in week 3. So we have PLC 3, and that's going to be for Friday. Usual format, quiz style, click in the answers, 3 attempts. Shouldn't be anything new there in terms of how it goes about. Homework 1 is due today by midnight tonight. And when I say midnight, I mean 11:59. So please be sure that you get that submitted. Along with that, quiz 1 is up and running. So hopefully you didn't try to take it in the very early morning hours because I forgot. Anyways, it wasn't available. Now it is, and so please be sure to take a look at homework quiz 1, and that's also before the end of the day today. So I believe I've got everything taken care of. If you are ASC, you should see 2 assignments. Just do the one labeled ASC and don't submit anything for the other one. There are multiple spaces, so I've assigned the quiz in one of the questions that's there, and then you should see 2 blank spaces underneath it. This is for everybody. In case you want to photograph and submit photographs and you have more than 1 page. So if you don't have more than 1 file to submit, please leave the other ones blank. You don't need to submit the same file 3 times. Sound good? So if you manage that and you have a PDF and you have just 1 thing, just put it in one and be done. If you have multiple files, I've provided multiple upload sites. Remember, your time does include the upload time, so please be aware of your internet connection and any potential distractions, and just tell them they gotta wait. After that, do we have anything else? Lab 2. Yes, Lab 2. Hopefully you have that done. Lab 2, that was kind of due yesterday. At least back when, for me saying this now, it was due already. It was due Monday, which was yesterday. So hopefully you got that done, and we can move forwards from there. A reminder, well, maybe this is not a reminder, this is brand new. Seeing as how we have here at Cabrillo, we have the holiday of the Friday the 13th and Monday the 16th. So both those days are holidays for us. Since I do post labs on the Friday, that means we have no lab this week. So we will have no lab Friday through the long weekend, and lab will pick up again the following week, which will be the week of, or the Friday the 20th. Okay, so lab 3 occurs next on 2/20, which is a week from this coming Friday. All right, so we have that holiday going. We don't have anything on Monday, so we have nothing to worry about there. And so that is that. I think that's all the administration stuff for us to deal with in terms of timing and due dates and things like that. Homework 2 will get posted likely a bit later today, and you can get started on that whenever you like. But that's going to be on a little bit of the stuff that we are going to start today, and a little bit later in this week we're going to start another topic, which is the wave model of light. So primarily homework 2 will be focused on that, though there will be some stuff on instruments. Alrighty, so let's get going on looking at optical instruments. So this is kind of a broad category and encompasses, I mean, quite a diverse selection of things. And we're going to do our best to try and describe these things using the Ray model. So let's go ahead and take a look at what we can effectively design or / interpret with the knowledge that we have so far. All right. Okay, so we've got under our belts mirrors, both plane and curved, and we've got lenses. And we've drawn ray diagrams for all of those. We've explored the characteristics of these objects. And so what we're going to ask now is what happens when we either use them singly for vision correction, or whether we use them in combination for a magnifier or the ability to see something far away or things like that. How do we modify what we have been doing in order to explain what we're seeing a little better, right? I haven't made a big deal about the difference between what we are calculating versus what we are seeing. But I think we're going to start taking a look at that today and tomorrow, and we're going to take we're going to look at how that's going to change. Okay, so let's go ahead and start off here with the simple magnifier, which is a bit of a review. Okay, but this is an important thing to have in your toolbox because we use it as a part of some of the other instruments that we're going to talk about, for notably the telescope and the microscope. So a simple magnifier is just a magnifying glass, right? Or a magnifying lens, if you like. Okay, so it's the situation where you have taken an object and brought it close to your lens. Okay, so here's our converging lens. The focal length, suppose, is out here. Hopefully that's reasonably symmetric. It looks like I'm a little short though. Yeah, I think I am. We'll go there. All right. So we've taken the object, we're putting it inside the focal point of the lens here. Let's suppose we're going to put it here. And we're going to draw our rays and see what happens. Okay, so let's take a look at that. I'm going to go with ray 1 coming in and going out. And I'm going to go with ray 2. Well, I'm going to grab my. I'm going to go with ray 2 here, coming down through about there. Oops. Okay, I'm going to straighten up ray 1 a bit. Ray 1 is not straight at all. Okay, something like that. Let's get rid of this. Okay. Just for smiles and giggles, I'll draw in ray 3, which is going up quite a bit here. Whoa. It's kind of going. Maybe I should move the object a little closer. It's up there. Wow. Coming out straight, right underneath here. Tracing it back is here. Tracing these back is here. These are almost parallel. This is pretty long. This is a pretty long stretch here. Where am I going? Wow, it's all the way back here. Okay, there we go. so there's our image way back there, but it's a simple magnifier, right? In other words, there's nothing else going on here. It's just that there's an object, and we've taken a lens and put it, when I say close, relatively close, within the focal point, right? The object is within the focal point, and I'm seeing an image of that object, which is huge, okay? And that is a magnifying glass. That's how the magnifying glass is explained as its operation. Therefore, when I am standing here and I'm looking at these beams of light, and you can imagine, I guess my eye is actually quite large because I need the one up here too. When I'm looking at these, also because of that, I should say this as a general rule. Notice that my lens was here, but then I drew this ray way up here. That is not meant to confuse, because you'd say, well, wait, the lens is right here. What's this thing doing way up here? Just imagine that you have the entire plane here. Okay, remember that we're talking about an approximation where we have a slightly small object and the lens is relatively small, and we're talking about the rays coming in relatively close to the axis here. So if I miss here, this is an artifact of the diagram. All right, this is something whereby I should just consider the middle of this lens to be large, and we're talking about the rays refracting at that plane, okay? So even if you miss as drastically as I just did here, that's fine, okay? That's fine. It's just a diagram, and it's meant to approximate what we have going on, all right? So don't worry if your lens is if you drew it too little, like I just did here, and you've got stuff going on, just kind of go for it, okay? Now, the light is, for me, in my eye, the light is diverging into my eye, and it's making an image that's large and over here, okay? Now, what I want to talk about is what kind of eyeglasses, or maybe I should say, for whom would this type of lens be good in an eyeglass? Okay, so people who are not able to see nearby objects. Okay, if my eye is over here, okay, and I guess my eye is quite large, and I've got, right, all these rays are coming into my eye. It's even bigger than that, but all these rays are coming into my eye, and what it's doing for me is it's taking this nearby object, which is here, and making it bigger and putting it over there, and that's something I can focus on. So if I have a problem trying to get my eye to see like really close up things, well, what I want is a converging lens in order to correct my vision, because what it does for me is it makes it large and it puts it a little further away, so that when I look at it and I don't have to squint and change my eye's focal length by right and squinting at something to try and see it. If I'm just trying to relaxed eye looking at it, it's going to be much easier to see, because instead of it being here, it's going to be here, and it's going to be big, right? So it's going to take up a larger portion of my field of vision. What I want to do for that is look at I want to look at two pieces of that. Okay. I want to look at two pieces of that. The first thing I want to look at is the idea of the eye being able to focus on things in a relaxed way. Okay, so again, if you ever go to the eye doctor, the optometrist, and they're going to say, okay, look at this, but don't squint your eye, just look normally, because they don't want you walking around with glasses having to do this all the time, going like, hey, what's this? Well, I can't see. They want you to just be able to put the glasses on and not have to squint your eyes and have things be in focus for your eyes. There is a point for pretty much everybody that is the nearest point that you can focus on without having to squint your eyes. All right, and if you imagine that the point for this eye, what if that point for this eye, the point where it could see things in a relaxed way without having to try and squint, What if that point was over here? And now all of a sudden I've got this thing, and you can try this out, right? You can take something, and well, I'm going to do this. You can take something and just look at it, and don't try to change your eyes. Just look at it, and what you'll find, there's a point where you're going to go like, okay, this is getting kind of ridiculous. Okay, and all of a sudden you're looking at it and you're going like, yeah, that's blurry, right? If it's like right in front of your face, you're seeing double. It's blurry. You're kind of looking past it, right? What you want is the point where you can just focus on the thing without having to really try, and that is called your near point. Okay, and most people's near point probably around 25 to 30, maybe about, say about a foot or so, about 25 to 30 centimeters. All right. Now, for some people, the near point is going to be much further away. In other words, everything within the near point is something that will appear blurry. Okay. And that means that this person is farsighted, right? The person has no problem seeing things that are far away, but when you bring things close, blur, blur, right? So what you're going to want to do is correct that with a lens like this. Because once something gets within the near point and it's looking blurry, what do you want to do? You want to take the image that is formed and stick it at the near point. And this is what eye doctors do. They go, okay, where's your near point? And what image is going to actually, I don't know if they actually do this. I doubt they do, because the machines look pretty cool and they just go, hey, what looks better, this or this? But what they are doing, this is the stuff that is the background to that. What they are doing is trying to assess, where can I put an image such that it will appear clear to you almost all the time? Okay. Anything that's too close to you, suppose you're farsighted, anything that's too close to you, it's going to be blurry, and you're going to want to see the image of that further away, because that's where you see things better. Okay. So you'll see people with reading glasses, for example, right? This is what the reading glasses are for. So when you want to read a book and you're holding it here and you're going like, I can't see this thing. And this, by the way, most of you probably are not going to be in this boat at this point in your lives. But those of us who are of the more cultured number of years, you will find that this is a thing where you're going to say, oh, I got to put my glasses on to read this book. Or they're going to say, here, they hand you a piece of paper, and you're going to see people go, okay, hold on. What does this say? Right? Like that. So that type of lens is going to be this. It's a magnifier, and it's one in which the image is further so that you can more relaxedly look at it without having to squint. Okay? So this approaches the correction for this is the lens appropriate for a far-sighted person. This pen is a little bit. Sorry, let me just rewrite that so you can see it a little better. Correction for farsightedness. Which I think goes by the technical name of hyperopia. You have the myopia is nearsighted and hyperopia is farsighted. So this is a correction for those who have the farsighted condition, because that's exactly what this lens does. It puts the image further away, and that's good for folks who have this. All right. So that was one of the points I wanted to make, was you have this thing called a near point. Okay. The near point, I'm just going to write this. Let me just write this over here. You have a near point, and the near point is the point at which you can, like I said, focus on an object without straining your eye. Okay, near point. And remember, this has to, you want to use a relaxed eye. This is kind of what I'm trying to get at. Glasses aren't, you don't want to put on a pair of glasses and have to squint all day. So the relaxed eye is is the operation by which we're going here. And you can easily find your near point, just like I said, just have an object and bring it closer until you're kind of going like, that's too close. I'm not seeing that right. About where is it? If I do this, right? I would say maybe about here. I can still read the writing on my pen. I don't know what's that. That's even there is even I'm working a little harder here, but it's really easy right here. Right? I have to squint I have to cross my eyes a little bit to get that writing, but if I'm here it's cool. So that's maybe about 11. That's almost I got a 9-inch span here and about another inch. So maybe it's about 10, 11 inches there. Okay? Almost a foot. All right? So this typically, I'm going to say typically approximately 25 centimeters. Okay? Around about 10 inches or so. When you grow older, that changes. Okay? It can for some people it goes further away. For some people it doesn't. And anyways, other things get blurry instead. All right, so this is one of the points I wanted to make, was that when you are trying to correct vision, one of the things you want to do is bring images to the near point. So here's a situation where this object is blurry to this eye if it was right here without the lens. Okay. When the lens is here and you get this image, now it's okay because the image is far away and larger. Okay, and I wanted to also address the largeness of this. Okay, let's suppose, just for ease of this drawing situation, let's suppose I'm going to look at how much does each object appear to take up in the field of vision of the eye. In order to make this easy, let's just put the eye at the focal point of this lens here. So we have a standard point from which we can operate. If we do that, then what am I doing? I'm putting an eyeball here, and I'm looking at how big does this object look in this eye's field of vision. The question is then, how do we measure something like that? We do it with an angle. So this is where there's a difference in what we've been talking about with magnification. What we've been talking about with magnification is when you take a screen and you put it, right, suppose we have a real image, take a screen and put it there, and then measure how big is the image on the screen. That is the magnification we have been calculating with our thin lens equation, our mirror, whatever the mirror equation is, that one with the reciprocals in it, and then that magnification, which is negative di over dl. That magnification is known as the lateral magnification. In other words, it's the magnification of an image as it appears on the screen, or as it appears if you were able to put a measuring device next to it were a virtual image. However, the issue for us is that is not what we see. We're not going to see a lateral magnification. We're going to see something different because our eye doesn't work that way. Our eye is a whole nother optical system. So when we're looking at what happens to the light going through a lens, right, and we can draw the rays out, this is what would happen if we were able to measure the image and figure out how far away it was from the lens. We would find all of this stuff. But this is not ultimately what we see, because when we look at things, we are introducing a whole nother set of lenses and refraction, which muddles things up a bit. Okay? So let me give you the quick and dirty way of thinking about what do our eyes see when we look at images that are magnified. Okay, if I think about the eye here, and I take this lens away, okay, and I just have the object here by itself, okay? There's no lens, just ignore this for a sec. I'm just wondering whether to erase it. I'm not going to erase it, but you're going to pretend that it's not here for a minute because we're going to bring it right back. Pretend that it's not here. If this lens was not here, how big would this object appear to us? Well, we can find that out. We can find that out because we have something called a field of vision. So the way our eye works is it takes light and projects an image onto our retina. Now, if the image is bigger, then we see a bigger image, and if it's smaller, we see a smaller image. But that depends on the angle by which we're looking at things. Not the angle but the angle of the size of the thing matters. Okay, I'll give you an example. We just missed it, but if you saw the full moon, what was it, like over the weekend or a couple of days ago? There was a full moon, okay? The full moon is, okay, it's big and bright and it's sitting there in the night sky, and if you have your thumb, you can cover it. You can cover the moon completely, right? You can just take, like this, and you go, oh, look, there's the moon, and you take like this, and you go, like I'm kind of covering over, here, I'll try and cover over the O. Oops, wrong way. Okay, here we go, getting there. I'm gonna go a little closer, and I'm gonna go the wrong way again. Okay, there, look. I'm just about covering the O with my thumb. Now, my thumb hasn't changed size, but it looks bigger, right? Why does it look bigger? Come on, there we go. Why does it look bigger? Because it's closer to you. It's closer to you, but it's the same size, which means it's taking up a larger angle in your field of vision. All right? So I could, for example, say, yeah, look, this thing's about the size of my pen, but when I bring the pen way up here, look, the pen's almost the size of the whiteboard now. Okay? It's more than the size of the whiteboard. No, it's just that it's taking up a bigger angle in your field of vision. So if you think about the moon, and you can say, oh, look, I can cover the moon. Is the moon the same size as your thumbnail? Of course not. It's really big, but it's really far away. Take that to another step. The moon covers the sun during a full solar eclipse. Is the moon the same size as the sun? Not even close. The sun is just really big, and it's really far away. But it takes up the same angle in our field of vision as moon does, and as our thumbnail held at about arm's length. Okay, so what's important for us is actually angle of an object as seen in our field of vision. Therefore, if I imagine what angle does this object take in my field of vision, forget the lens for a minute. What I'm going to do is say, all right, well, the angle this thing would take in my field of vision would be about measured from the axis here, right? The angle that this object takes in my field of vision would be about that much. If you can see that. Right, to the two dark lines here. This angle right here is how big this object appears in my field of vision. Okay, now throw the lens back in. Okay, now how much angle does this image take up in my field of vision? And I think I can convince you it's going to be more. Reason being, because I've got this angle right here, this ray right here, which I had to trace back. Right, here comes this ray right here in parallel with the axis going down through the focal point, but my eye is on the focal point. So this right here is the angle to the top of the image. Therefore, the image angle is really, if I just kind of darken in these dashed lines here, this one here is the angle of the image. In other words, that's how much it's going to be magnified. So I'll label this as object angle. and this one is the image angle. Okay, and I think I can convince you that the angle created by that larger image is bigger. Can I convince you of that? Here is the, right there to there is the image angle, and there to there is the object angle. Can I convince you of that? Like there to there? So what we have now is the ability to talk about a magnification which is more appropriate to our seeing than the lateral magnification is. All right, so the angular magnification is born from our perception of how big something appears because of how much angle it takes up in our field of vision. And anytime you're kind of thinking, well, wait a minute, what's going on? Just remember that you can cover up large objects by taking a small object and holding it really close, right? Just like I did, right? My thumb is nowhere near the size of this O, it's nowhere near the size of the moon, but I can cover those objects up because in my field of vision, that's the same angular size. It has nothing to do with how big the actual object is. It has to do with how much angle the object is taking up in your field of vision. So this is known as the angular magnification. And the angular magnification is exactly what you think it would be. It's just the dividing, it's the ratio of the angles. Okay, so I'm going to take the image angle, theta of the image, and I'm going to divide by the theta of the object. Okay, and I'm going to call this capital M. Except I'm going to do it with a better pen. Let's try to do this. Let me rewrite that. This is going to do it. All right, I'm going to call this capital M. Maybe I'll just put little feet or something on the M so it's not the same as little m. Remember, little m, our lateral magnification was that, but that's what we would measure on a screen. That's not going to work for us if we want to think about how big does it look. As soon as you want to talk about how big something looks, you got to peer this thing up over here. Okay, you got to use that. Okay, so this is the magnifier, and it's a vision correction, and we've hit the near point, and now we've hit angular magnification. These are all critical components to kind of putting together how to look at the images that we see. All right, I'm going to do one more example here, which is the nearsighted person. So if you want to correct your nearsightedness, how do we do that? Well, what do you suppose the chances are that we've talked about two types of lenses and there's two types of vision corrections? Maybe let's try a diverging lens for the nearsighted folk. Alrighty, let's try a diverging lens for the nearsighted folk. Okay, nearsighted folk. Let's try this again. Now, if I've got here let's do this. We're going to put in a diverging lens. I need it to be a little bit larger than that, so let's do this. Okay. And now I've got about there. Now, if we just put an object here, suppose that we've got a faraway object. I'm not going to use that big, huge thing as the faraway object. All right, but suppose that I've got a faraway object, and it's way over here. Okay, here's my faraway object. If I am a nearsighted person and I'm looking at this faraway object, it is appearing blurry to me. What do I want to do? I want to bring that far object closer, maybe towards my near point, where I can focus on it more easily. Okay. Now this is a situation where you're going to sacrifice some of the height. You're going to sacrifice some of the magnification. Okay. So if we draw just a regular ray diagram for this situation here, I'm going to do. If we just draw the regular rays, just like we have been doing, so we've got a paralleling coming here, like so. This is a faraway object, so so we've got ray coming in like that. We've got a ray coming in like this. Here's ray 2 going through. Let's go ray 3. I'm just going to take care of all of these while I'm over here. Here's ray 3. Okay, like so. Whoops. Okay. All righty. Ray 1 is going to go like this. Whoops. Come on. There you go. Ray 1's going like that. Ray 2 is just going to continue that way. Ray 3 is now going to continue this way. Like that. And so my eye, which is over here, is looking at these 3 diverging rays and saying, okay, where's the image? The image, right, is where this one crosses with, I didn't draw this one back, but you can see it's going to be right about there. And this is ray 2. So my image is here. Okay. So the image is there. If our eye, this is a little bit harder to see, but first let's concentrate on the near point. This is why a diverging lens is appropriate for nearsighted people. You take the faraway object, I can't see it, it's blurry. The lens is going to make an image such that it's closer. And if this is about where your near point is, then great news. Okay? You can now see this image as it's, you could see it with a relaxed eye, right? You should be able to see it fairly clearly if your near point is whatever distance from the lens you are here. Okay. So let's take a look here at the same type of thing. It's not quite, let's just do the same type of thing. Let's suppose we put the eye nearby the focal point here and we look at the magnification, right? Hopefully I was able to convince you in the last case, the converging lens had a larger than 1 magnification because the angles were that way. In this case, you're going to see, right? And then I'm going to go from here and then I'm going to go up to there. Like so, right? Just about along this line right here, because that would have gone through the focal point here. So it's the difference, hard to see this one, but it's the difference between, that's your image angle right there. And then your object angle, whoops. Flip that around. Never mind. This is your object angle. There we go. This is your image angle here. All right. It's maybe a bit tough to see because of the busyness of this diagram, but it's this line right here. I'll darken it. It's that angle right there. This is the image theta. And I think I can convince you that that image theta is less than the object theta. So you're going to see something that's less big than than normal, but it will be clear. Okay, it won't be fuzzy, it'll be clearer, right? And that's ultimately what, in my case, this is what my glasses are doing. I'm looking, for example, I'm looking out the window. I know there's trees out there, I can see them, but they're very blurry. And so when I go like this, it's what you go, oh yeah, they're still right there. They're not really just right there anymore. It's making an image of those, which is right in here somewhere, right? Where I can see them with a relaxed eye and not have to go like, eh? Okay. The diverging lens brings the image in, and this is appropriate for nearsighted folks. Okay, diverging lens is the correction for nearsighted. I will also say that this is fairly simplistic, what I'm talking about here. Okay, this is fairly simplistic. This is the bare bones of lenses, because there's a lot of other things when you get into the nitty-gritty of what's going on with the lens and how does it bend the light and make the image and da-da-da-da. There's a lot more going on here, okay? But fortunately, if you're really interested in that, there's something called optometry school, and you can go to that. Also, by the way, fantastically interesting subject, of which I understand barely some. So by no means am I an expert on the nitty-gritty of this. But anyways, with broad strokes, we're going to use diverging lenses as the near sight correction, because ultimately we are concentrating on what is going to look clear at our near point, and this is what's going to do it for us. Okay. Gosh, I was going to say something else pretty cool about that, but I forgot what it was. So we are going to move along with this. All right. What I want to do now is take a look at lenses in combination. Now that we've established single lens as a corrector, and we've looked at both of the types of lenses as a corrector for vision, and we've talked about some of the vision things, I want to look at what happens when we have two lenses in combination. Let's start by just doing a regular ray diagram and analysis of this before we start putting in the question of what does it look like to us. Alrighty. So let's take a look at a ray diagram. Excuse me. Let's take a look at a ray diagram. Let's suppose that we have two lenses, almost as if it's maybe like a camera or something. Okay. I'm not saying it is, but let's just suppose we have I'm going to start this way. I'm going to start with a diverging lens, and then we'll flip them around. Diverging lens, okay, like this. Okay, and we're going to have a converging lens kind of close in here. Whoops. Whoa, all right, converging lens, maybe a little bit bigger than that. Okay, like so. Let's suppose that the focal length of the converging lens is about equal to the spacing of the lenses. Okay, so let's say that the focal length for this lens here is right there on top of that lens. So the red one is focal. The red one is the focal length for the converging lens. I'll call this lens 2. But I'm going to do that with a different marker because that one's not showing up too well. All right, so I'm going to label this as F2, and F2 is inside the diverging lens because the diverging lens is sitting right on top of the focal point for the converging lens. All right, let's make the diverging lens have a relatively short focal length. So perhaps the focal length for the diverging lens is going to look maybe something like, let's just put it about there. I'll call that F1, from there to there, F1. Alrighty, suppose we have an object that we are interested in out here. Let's see what it looks like. If I have an object over here, what do we get when we're looking through both lenses? Okay, in other words, what's the final image? The key here is to do one at a time, just like we have been doing. Take them individually. I'm going to do a ray diagram and tracing through the first lens here based on the two focal points here and here. And then I'm going to take that image and use that as the object for tracing the rays through here on lens 2, using that and that as the focal points. All right. So it may seem somewhat strange, but ultimately it's using what we've learned and just putting them together step by step, okay? So let's take a look at this. And then we can, let's do the ray diagram first. We'll throw some numbers into it and we can try to do a calculation later if you like. Before we start, I think I mentioned at the beginning of the semester Wheeler's first principle, which is don't calculate until you already know the answer. So this is a little bit of a side road to that, but let's not draw until we already know what we're looking for. Okay, so what is it that we're going to find? Okay, here I'm looking at object with diverging lens, and so the ray diagram is going to be exactly what I just erased from here with the near sight correction, right? It's going to be a virtual upright image on the same side of the lens as the object, right? It's going to be somewhere located in here. What that means is it's going to be outside, okay? If the image is located in here and I'm using that image as the object for my converging lens, then this image, which is going to be the object, is now outside the focal point for the converging lens. Because remember, the converging lens focal point is right at the middle of this diverging lens. Since the image formed by the diverging lens is going to be within its focal point, within its focal length, that's outside this one. So I'm going to expect an object which is outside the focal point of a converging lens to form a real image on the other side of the lens over here. And it should be real inverted. And in this case, I'm going to say it might be slightly magnified from what it was. But we'll see, because the diverging lens is going to minify it somewhat. So it might be offsetting situations there. We'll also deal with how to deal with that. We'll talk about what's going to happen with the magnifications. All right, so let's start with just a regular, all the same stuff that we have been using. Okay, never mind the angular stuff for just a minute. We'll deal with that when we get to a slightly more complicated situation here. All right, so let's start here. I'm going to do a ray coming in here. Let's choose. How's that showing up? Not too bad. Maybe we can use this. Orange I don't usually use. Okay, that's going in there. Yeah, I don't really like this. It doesn't seem dark enough. Let's do this. I've got ray 1 going that way. So unfortunately I started it in orange, so I'm going to finish it in orange. Ray 1's going this way. Here it's coming out like that. Okay, I'm going to dash it back to the focal point like that. So that's where I know my image is going to be located, somewhere within this dashed triangle, because this is ray 1 and you know we love ray 1. So ray 2 is coming in here. It's going to go straight through the middle of the lens right about there. So I could say ray 2 is coming in like that, leaving like that. Okay, so right now I have enough to do my to capture my image. I'm going to go ahead and draw ray 3 just for smiles and giggles, and have that be here, coming in like that, and then leaving parallel like so. All right, so these are my 3 outgoing rays, 1, 2, and 3, like so. And we trace them back to find that they make an image that's just relatively small, and it's right here. All right, it's right there. That is a very small image, and I apologize if you can't quite see that, but there it is nonetheless. I'm going to call that image 1. Image 1 is now object 2, and we're going to have a very small, very small object here. But notice a couple of things, okay? Notice a couple of things. We're done drawing the ray diagram and finding the image for the diverging lens, for lens 1. Now I'm going to concentrate on what happens to lens 2. As I have drawn it here, I don't have to do a lot of work because I've already got a couple of rays in place to help me where the rays are going to go and create the image. Where's the final image going to be? It's going to be over here. Okay. And now take a quick look at these rays. Ray number 2 from the diverging lens passed right through the focal point here. Okay, so it's going past the object. So it's going from the object through the focal point. So we already know that that's going to be a ray that we can use here in the converging lens. If I take the object and I look at the ray that goes from the object through the focal point and then to the lens, it comes out parallel with the axis. So this one, I can just continue this ray and find out that it goes like so into the converging lens here and then comes out parallel with the axis like this, like that. And you'll notice that that is the hallmark of the converging lens, right? It's bringing rays together, right? Converging lens. Make sure, I've still seen folks falling for the situation in the diverging lens case. Parallel incoming going down through the focal point. No, no, no. Remember, this is a diverging lens. It's spraying stuff out. It's getting stuff away from other stuff. Okay, so it comes in and you want it to make a diverging situation. Okay, so please practice these ray diagrams. They are important. There you go. Hey, I'm going to look at this ray here. It's already parallel on its way in towards lens 2, and so I'm going to continue that straight into lens 2. It's going to come here, and now it's going to go out via the focal point, which is here. Oh boy, I got a long way to go. Maybe I'll find it. Here comes the other one. Here comes this one. There it is. Okay, here's the axis. Here's the image. It's right there. This is image 2. Okay. So let's think about what we've done here. We have taken the diverging lens and we've thwarted it, completely thwarted it. Because the diverging lens is trying to take the rays and, right, like this. But this converging lens is saying, no, 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 bring them back, bring them back. And it does actually end up making the real image right over here, okay? Which is great. I mean, if you are trying to take a photograph of something, this is what you ultimately want, okay? You are taking an image, which means you are expecting light to be impinging on some type of surface here, whether it be old style photographic film, whether it be a CCD or some type of array of light sensors, right? You are expecting a real image on that. That is a screen by which light creates an image and then transports it, and you say, oh, look, this is what I'm looking at. So this appears to be a ultimately slightly minified It's almost the same size as the object, but ultimately probably a little smaller because of the effect of the diverging lens here. Final image is what I was going to say. So let's take a look at this. Now, I want to make a couple of points about this. When doing a situation with two lenses or a lens and a mirror, it is not always the case that you will set up such a great little situation here like I did, where I can take rays that I already used to make image 1 and continue them to find image 2. That's not always going to be the case. However, I do want to address this point. Were I to draw the rays to find image 1, I then, in my mind, am throwing away this lens, I'm taking this image and I'm clicking it into, this is now an object. What happens with an object? An object emits light in an infinity of directions with an infinity of light rays. Remember, we only pick 2 or 3 that are convenient for us to draw. So, should you run into the situation in which these rays that you used to find image 1 do not correspond to any cool rays that we could use right away, don't use them. Use regular rays and be aware that, yes, you're picking rays that don't seem to continue. For example, if I took a look at like this light ray here, this light ray, when it comes to a converging lens, I don't have any information on this light ray. I don't know what the converging lens is going to do with it. It's not one of my cool, easy rays, right? For example, I had, for lens 2 here, I had a parallel incoming, and it went to the focal point. I had a from the focal point parallel outgoing, so I covered those two. What about the other one? Well, it goes straight through the lens. Where's that one? Well, I could draw that in because that's a legitimate light ray, and that light ultimately will be there. It's just that we haven't drawn it in this situation. I could draw it. So I can, in the case of having an image that is made, I can now originate a brand new light ray from the top of this object, which is now my object, and going through the middle of the lens, right? This blue line here. Hard to see. Sorry about that. I could originate a brand new ray that does not connect to any of the other light rays. And I really want to make a deal out of this point. It seems like I'm belaboring the issue. At least to me it does, because I feel like I'm repeating myself. But I want to instill the idea that we haven't drawn all the light rays. So starting a light ray here that wasn't one of the ones that made it is totally okay, right? I'm now going to use that light ray to go through lens 2. It's there. I just didn't use it from lens 1. Okay? So it's okay. Let's now go through the math analysis of this. I'll throw a few numbers in and we'll try to figure out what to do as we go along. One of the things you might ask is, okay, how are we going to find out where image 2 is? Well, we have these two lens, these lens equations, the object, the image object, whatever you call this one, and then the magnification. And remember, I'm not dealing with angular because there's no eye involved. This is the only time you use angular magnification is when you're looking at something. Does this appear to be magnified? Right now, I just want to consider the lateral magnification. That's this one. I want to apply both of these to find image 1, and then I want to apply both of these to find image 2, ultimately. All right? So how do we do this? Let's suppose that this is a little more than halfway. So let's suppose we've got a focal length here. Let's suppose the focal length of lens 2 is, let's call that 10 centimeters. And of course it's positive, I'm not going to put the plus sign on there. Let's consider the focal length of lens 1 to be, it looks like it's about, it looks like it's about half that distance. Maybe a little less than half that distance. I'm going to go with half. This is a diverging lens. I'm going to go with a negative 5 centimeter focal length. Alrighty. Now, what is also a crucial piece of information is how far apart are the lenses? Because thinking into what I'm about to go for here, I want to find this image distance, no problem. I'll deal with that from lens 1 easily enough. But now I have to say what's the distance from that image to lens 2. That means I need the lens spacing. But we have that covered because the lens spacing is the focal length of lens 2. That again is a special situation that I've created here, but in general, the lens spacing is something we would need to know. Let's take a look at a quick analysis for lens 1. Lens 1, let's go right here. So lens 1, I'm going to find my image by going focal minus object. All right, so this object is fairly far outside. I just wanted to take a quick, so that's the 2F point. So that's 10 centimeters away from there. And then it's another one of those, which is a little more than that. Let's say, oh, I don't really want to do this, but I'm going to, I guess. Let's go with 15 centimeters. Let's go object distance of 15 centimeters. Okay, so I'm going to say that this thing here is now 1 over negative 5 minus 1 over 15. Okay, remember to keep your negatives in the focals. If we do that, I'm going to get 3 over 15 minus 4 over 15, which is 15/4, so it's 7.5 divided by 2, which is 3.75. Is that right? Seven and a half divided by 2 seems like 375. Yeah, that seems okay. That tracks. This is a fairly small distance to the image here. Okay, it is within the focal point of 5 centimeters, so that tracks. You will notice that the magnification is going to come out pretty small. Okay, so for image 1, it's there, and the magnification, which is di over do, I've already written that, don't need to do it again. It's negative 3.75 over 15. So that's going to be a positive. That's a little more than 1/5. That's 1/5, and then that's, so it's 0.2. Is that really 0.25? No. Yeah, it is. Of course it is. It's 1/4. 0.25. All right. So we have a 1/4 image. That's, I mean, it tracks, right? It's small. I don't know if it's a 1/4, but it's pretty little. That is therefore, I'm going to call this magnification number 1. This is M1. Okay. If I want to go now and take that image, change it into the object, and now hit lens 2, what I have to do now is go to lens 2, and I have to say, okay, the object is outside the focal point of lens 2, and what is the distance that it's going to be from lens 2? Because my first task here is find that image distance. The focal length is 10 centimeters. What's the object distance? I said image distance. What's the object distance? It's 10 plus the 3.75, because that 3.75 is away from here. So this is 13.75 centimeters here. What does that give us? Okay, I don't think I can do that necessarily in my head. 13.75. It's going to be some number. All right, hold on. I'll see if I can calculate it real quick. Let's find a calculator and let's do this. So let's go 1 over 13. No, let's go 1 over 10 minus 1 over 13.75. And now let's do 1 over that. And that looks like it's going to be 36. I'll just call it 36 and a half. Okay, I won't. Yeah, I know you're probably screaming at me. Okay, it's 36.7 centimeters. 36.7 centimeters, that kind of tracks. It's way out there. I don't know if it's 3 times that distance. 1, 2, 3, 4. No, it's not. But okay, it's far enough outside the focal point that we should be pretty convinced that it's far enough away based on the ray diagram. Let's look at magnification number 2. M2 is the same, minus di over do, and I have di minus 36.7, and that's divided by 13.75. Gosh, that's going to be about 3-ish, say about 2.8. I don't know. Let's say it's about minus 3. Okay, I'll put minus 2.8. I don't even know if that's correct. Let's do 36 divided by 13.75. See what that comes. 2.7, 2.8, 2.7. Boy, I was close. Pretty good. So that's magnified 2.7. All right, so now here we go. What's the final image? Okay, so the final image you can say is 36.7 centimeters away from the second lens. Okay, that puts its position in space. When you talk about the magnification overall of the image, we now have to multiply the 2 lateral magnifications together. So I need to do lateral magnification total. Let's do total being M1 multiplying M2. And that means I'm going to take the 2.7 and I'm going to multiply by the 0.25. All right, so what does that mean? We're going to find something around, that's half and then half again. So we're talking about something that's around 0.7. So it's definitely minified compared to the object. All right, this is going to end up, I got to erase this here. This is going to end up at plus 0.25 times minus 2.7. And that's going to give us a number, and that number is going to be negative, which is good because the overall image is flipped over compared to the original object, okay? So that's going to be an overall negative number. It's going to be about half or so, not quite, but about. And that didn't quite track with my original, but okay, that's the way it is. Like I said, this is often the hardest quantity to analyze or to try and assess if you're looking at the ray diagram solely for information. It gives you most everything else, right? The orientation, the approximate distance, okay, that type of thing. The magnification can be difficult to accurately assess solely from a ray diagram. So remember, we're going to multiply these two in order to find the total magnification when going through multiple objects. Multiple components, whether it be 2 lenses or mirror lens. Okay. All right, sound good so far? Great. So let's do this. Let's do this. I want to now consider taking a 2-lens system such as this and now introducing angular magnification to it. Okay, I spent that time talking about it and you're going like, well, where is it? Okay, let's talk about the angular magnification. This situation here is not really a candidate for angular magnification because it's not really doing anything for us. Okay, let's consider a situation in which the angular magnification is appropriate because the lateral magnification doesn't have much meaning. Okay, and I'll show you what I'm talking about. Let's do this. Okay, let's do this. I'm going to use a simple magnifier. Okay. Now, that by itself hopefully is a bit of a tip-off because we started talking about the simple magnifier, and that's when I introduced magnification, angular magnification. Okay. So here's a case. Let me show you this case. I've got an object, and it's pretty small. It's gonna be right about there. Okay, so here's that. Now I want to look at this object. I would like to see a magnified image of this object. So let's suppose that I take a lens and the lens has a focal point which is fairly small, fairly small. So let's suppose that it's just outside. I'm going to have this object. I'll make the object bigger, I'll tell you, so you can see it. I'll make the object slightly bigger. Okay, I'm going to put the focal length basically like right next to it. And I'm going to have my lens, say, right here. Oops, that's not a very symmetric lens. I should maybe try to do a bit better than that. It should go to here, like that. All right, so I'm going to take my lens, and it has a focal point which is really small. Okay, this is the focal point. So here, f1. There's f1 right there. What's this going to do? Well, this is going to magnify the image, right? Because you know that the closer the object is to the focal point, the larger the image is going to be, especially when it's converging, right? It's going to magnify. So, real quick, I'm going to take a couple of sketches here. I'm going to come in parallel, go out through the focal point. Yes, I'm going to use it. It's here. For goodness sakes, I will do that. Okay, so here we go. Down it goes. Okay, now I'm going to do the one that goes straight through, and that's going to end up about there. Like so. The one that goes out through the focal point, just to see if I got anything reasonable here, goes, oh yeah, that looks pretty good. I missed it a little bit, but that's okay. Let's just suppose it's about there. Okay, so the image is going to come out here. All right, so there's image 1. As you can see, as you would expect, this object was outside the focal point, and it produces an inverted, real, magnified image on the other side of the lens. This is what you would expect. Nothing different. This is a standard ray diagram for a lens with an object outside the focal length. Now I've decided, cool, but that magnification is not enough. I now want to take a simple magnifier and magnify this image. Okay? So if I'm going to do that, where am I going to put the next lens that now is going to be my magnifier? I basically want to take this image, which is already expanded a little bit, and blow it up even more so I can really see it. Because maybe this thing is really small. Maybe this is a really, really small object. It's like a dust grain or something. It's really tiny. I need it to be magnified quite a bit so that I can see it. Now I'm going to take a simple magnifier and I'm going to say, all right, how do I magnify an object? Or how do I magnify an object and get a really large image? What do? Well, if I want a really large image, I put that object right on top of the focal point. Now it's too far. All right, now is it too far? 1, 2, 3, 1, 2. No, yeah, it was too far. Okay, so now I'm going to take this thing. Here's focal length 2, and here's focal length 2. Now I'm going to take a lens with a focal point, and I'm going to put that object, this is my new object for this lens, I'm going to put it so that it falls right on that focal point. Okay, let's just real quick draw the ray diagram for this. Okay, look, you know I'm going to have one going parallel out. Already got that one, it's here. Out through the focal point, like so. And I've got one going through the middle of the lens like so. Like so. Okay, look at these now. Look at those. These are parallel. Where's the image? You see, this is the problem. Okay. This is why we need, or this is one of the reasons we need angular magnification. Here's the trick. Okay. Here's the trick. This is the thinking. If I say, well, where's the image? I mean, maybe they are kind of converging a little bit, but the image would be big and it would be way over there. Okay. Here's the thing about our eyes. Well, wait, let me back up before I tell you that. If I just use lateral magnification, here's why it won't work. The DO is about equal to the focal length, right? That's my object distance, focal length. But the D image is going to be darn near infinity, because if I look at this thing here and I go, where's the image? If the object is on the focal point, then 1 over f minus 1 over f is 0, and therefore my image distance has gone off to infinity, right? D image is going off to infinity, and therefore the magnification is going off to infinity. We don't want to deal with infinite numbers. They're too big. Now, since the lateral magnification is infinity because the image is infinitely far away and infinitely large, here's the fun way of thinking. We can still see it. Isn't that great? Because remember, our eyes are another optical system. These rays may not converge and they may not make an image themselves, but when they enter our eye, because they are parallel, they will converge because we have a converging optical system in our eyes. So we can see objects that are infinitely far away and infinitely large. Example, the sun. Basically, that thing is infinitely far away and infinitely large. And we can see it, right? But, by the way, don't look directly at the tip from me to you. I can see it now. Hey, I'm going to go out and look straight at the sun for like 5 minutes. No, don't do that. Just regard it, right? Just know that you can see it, okay? So this is where the angular magnification comes in handy, all right? Now I can say, look, if I can look at the object and the image and the angles that they make, then I've got an image right here. I've got an image angle right there. Okay, that can be my image angle. If I consider my eye to be basically easy enough, right, set it at the focal length of this lens right here, then the angle is the angle of the object, the angle of the image is really that same angle right here, right? That's a parallel angle. And the object has an angle which is less than that. So I'm going to erase this and I'm going to draw this in here, right? This right here is the object. That's the object's angle. So we're getting a good magnification here. When we do that, we're going to use the angular magnification because we've got a simple magnifier, and we cannot use the lateral magnification. When I want the total magnification of the entire system, I still go back to multiplying them, but now one of them is an angular magnification. Okay, so I'm going to look at the magnification through lens 1 as a standard lateral magnification, and then I'm going to look at the angular magnification through the simple magnifier as M2, and I'm going to multiply those together to get the total magnification of this two-lens system here. This is the basics of the microscope. Okay, you've got an object which is really, really tiny. You project that image out here down a long microscope tube, and then you take an eyepiece which has a very short focal length, right, such that the image forms right on top of it, and that blows it up. And this is why when you look at the microscope and you go, oh, I want to look that way, you got to move the other way because the image has flipped over compared to the object, right? So this is the essence of a microscope and the use of the simple magnifier. Okay, so that's why your microscopes often say 40x, right? That's the angular magnification multiplied by what you're going to get out of the lateral magnification of the first lens. Or you might have a 40x eyepiece. All right, same idea. But anyways, I think that's going to do it for today. We have talked about that. We'll come back tomorrow. We'll talk a little bit more about some other systems that magnify and that we can use angular magnification for, and do a couple of examples. And I think that's probably all we're going to do for instruments, and that means on Thursday we're going to move into the wave model. So stay tuned for that. Have a great rest of your day. Don't forget, homework due today, quiz today, everything's today. Homework 2 is going to start off tomorrow. Have a great rest of your day, folks. See you later.